remember, hypothesis is a presumption that you're investigating.
This one maybe is pretty
So, all the tests that you are doing have a hypothesis. All the descriptive statistical tests you are running, all the relationship tests you're running have a hypothesis. You should read up the hypotheses under each of those. Okay. If it was the test for normal distribution, okay, Shapiro-Wilks, it has its null hypothesis, it has its alternative hypothesis. That is what you're investigating. Okay. So the null is stated in the negative manner, whereas the alternative hypothesis is stated in the positive. So in this case, you'd be looking at investigating there is a relationship between the variables, or the variable is normally distributed. Okay? Distribution is what you're investigating. Okay? And all tests have to have the hypothesis. Okay. I don't bog down this much at the first year, first semester scenario because you have to have more data science experience. If you have 100% accuracy, as I've written it here, it is not possible to have an alpha of 100%. You may have 99.99%. Okay? And perhaps you have that high that it's not possible to accept a hypothesis. Therefore, we select a level of significance that is usually at 5%. Why we select at 5% means that we have 95% confidence in our result. Okay? The 5% is the margin of error. Okay? So we usually state our alpha at 5%. You will see this alpha also written a lot of the time as a decimal or as a ratio, 0.05. Okay? At 0.05 alpha, I find that this hypothesis can be accepted that the students of this class and so on based on what it was you were investigating. We then also have the p-value, which is why we started by working probabilities. The p-value is a calculated probability of finding the observed results when the null hypothesis is true. Okay? What is the probability that these results we have gotten that illustrate a particular variable as being normally distributed? What is the probability that they fit to the null hypothesis of being normally distributed? Okay. This p-value is very, very important. And we always, with every statistical test, have to have the p-value. Okay? This part is the most key. But to calculate the p-value, we must first set the level of significance or the alpha. Okay, and we usually set it at 5% or 0.05%. Then, depending on the statistical test you are working with, okay, so this I have put as test statistic. The test could be an ANOVA, it could be a correlation that you're working with, Pearson's correlation. Okay? This statistic usually gives you a value. Okay? You know your correlations will give you values ranging from 1 to -1. Okay? You know your covariance values will give you which values? Covariance. Covariance. Another relationship statistic. It will give you values that range from negative infinity to positive infinity. Do you remember this? No? I can read that one. Okay. So you have these different statistical tests and they give you particular values, okay? So you kind of get conversant with which statistic presents which value, okay? So these results can be compared to a critical value or a p-value that is attached to them in order to make a decision as to whether you accept or reject your null hypothesis. Okay? But always first look at how the null hypothesis is stated for each statistical test. Okay? And those different critical values of the p. Now, the p's can range from 0 to 1. Okay? You have to see for each test where that cutoff point is of alpha. Is it at 0.05, illustrating anything that is less than 0.05 is statistically significant? Or is it at greater than 0.05 if it's an alternative hypothesis? Okay. So you need to go and read those, but they are also part of the exercise of type 2 errors, type 1 errors, as p-values are very clear. Okay. Okay. Then there is another statistical aspect, a critical value, but you can also look at this as the confidence interval. Then we also have the degrees of freedom, and these look at variability. Okay. They are also related to the sample size and determine the shape of your data set. The shape being how many variables you have, how many samples you have within that data set. We won't handle degrees of freedom much in this section, but I know you did have it. Did you have it in high school? You never used any logbooks? With no degrees of freedom? Yeah. No degrees of freedom. All times have changed. So we will handle this bit in your second year, looking at the degrees of freedom a little more in depth. Okay. So, how do we then, in a scenario, carry out hypothesis testing? Okay. If you have questions, please ask or put up your hand. He's not the only individual that can pose a question. We also have questions. Right? Okay. So first we state and define it. Are we stating it in the null format? Are we stating it in the alternative format? So be certain with each statistical test you're working with, how is it stated? Okay? Is it null? Is it alternative? You need to know what it is you're investigating. Then choose the significance level, or the alpha, 0.05 or 5%. Then one goes ahead to do the sampling, okay, with those sampling techniques, and then you can run your analysis, carry out your test statistic and a corresponding p-value, and then make a conclusion based on the hypothesis. Within Python, there is a library called SciPy. Okay, SciPy stats. So it has a lot of the statistical tests. A lot of the statistical tests that we use for descriptive statistics, inferential, and even predictive statistics. So it does have some aspects of machine learning as you will go on later with your courses. Okay? So I brought in these two data sets and I want to investigate a hypothesis. Okay? And I'm looking looking at particular statistical tests in my hypothesis testing. One of the tests I'm looking at is a t-test. So you should look up what the hypotheses and assumptions for a t-test are. So this one compares the means of two different samples. Okay? For instance, I will have class A plus B, and I want to compare the means because I'm going in with the assumption that the average maybe grade is the same. This is what I'm investigating in this t-test. Okay? And this test can only be used on data that is normally distributed. So now you see where the errors can come from. If you apply the wrong test to data that it doesn't work with, you will get errors. And there are different types of t-tests, okay, that you can look at. And those can also determine what you use, okay? One of the other limitations this t-test has, it can only work with 30 or less than 30 samples, okay? And also those samples must be more than two or more, okay? You can't just have one sample and you're comparing sample 1 to sample 2, okay? So you must at least have 2 samples in each of those groupings. Okay, so if you have a one sample t-test, this will look or compare the means with a known mean or average. How would this scenario work out? There is assumptions about height in the world based on gender. Okay? I think the last I checked, it said the average height of a female is about 5'2". Okay? But apparently these levels are going down because there's a lot of malnutrition and aflatoxins that are making people grow a lot shorter, especially in Africa. Yeah. This is not targeting anyone. It's fine, I'm also short. So if that is the average we are using, okay, as the global population average. But then now we take down our numbers in here, keeping in check that we only have to include 30 samples, okay, no more than 30 samples. And we want to compare that mean, okay, the 5.2, to what we have in here, okay? So that's the population mean we are comparing to. The null hypothesis would be stated as the average, okay, or the sample mean, okay, is equal to the population mean, okay, which the alternative will now be the reverse. The sample mean is not equal to the population mean. So you want to now investigate that. So that is where a t-test can be applied. But it has its limitation in numbers, so there are other types of statistical tests that can be applied that allow for more numbers, but carry out a similar test or investigate the similar question, okay? Those I will let you read up. Okay, so for instance, in this situation, let's say I'm working with random sample, okay? So random is a library in which we can generate different random variables or random data sets, okay? So it allows you to generate different aspects, okay? So close that a bit. And here we want to use random data and make it fit the assumptions of a t-test. Firstly, the t-test wants that data to be normally distributed. Okay? And then also stick within those numbers as stated. So we're having 2 samples here. We are having A and B. And in A, which is now our variable or a list of samples, we are using random the library dot Gauge to ensure that these samples are in a Gaussian distribution. Okay. So here it will apply its own means and its own standard deviations that are default for it to be normally distributed. And we're ensuring that the range remains within 30 samples. Okay. So let's say we assume the population mean is 40. Okay. The null hypothesis is that the sample mean is equal to the population mean of 40. We set our alpha at 5%. So anything that has a p-value of less than 5% or less than 0.05, we will reject the null hypothesis, meaning the sample mean will not be equal to the population mean of 40. Okay. So how this test is run is we call out the t-statistic, okay, and the p-value. Remember the t-statistic being the statistical test output value and the p-value that we're interested in. And then from stats, okay, which is in under SciPy stats, we call for t-test underscore one sample, which is the one sample t-test. We then have our sample A, okay, and the population mean, and we generate that output, okay? So once it generates the output, we have our t-statistic as 3.3. Our p-value is 0.002, so it is much, much less than 0.05, okay, or 5%. And it also generated for us the mean of that sample, or that sample group A, which is now 50.19, okay? So we can see 50.19 is different from 40 of the population mean. But what helps us have confidence or statistical credence to this difference is our p-value. And our p-value is showing that it's less than 5%, so we reject the null hypothesis. Meaning, our sample mean for sample A is not equal to or is not the same as our population mean. And we only say that confidently using the p-value. What if this p-value was greater than 0.05? Okay, but you're seeing the means are different. Okay? That would show that in as much as the means are different, statistically, there is no significant difference between them. So this is why we apply these p-values. Okay? They attach that statistical credence. They are more important than just the statistics or the values that we generate. Right? Okay, so let's see what sample B looks like.
What if my p-value is 0?
What if your p-value is 0? 0 is less than 0.05. Yeah.
So what would be the difference between
You have to set, you have,
0.0000 and as far as that is 0.002? What would be the difference between those two?
it's about where you have set your threshold. If you've set your threshold at 0.05, okay, and you're saying anything less than, so you have to always state it. Look. And you say here anything less than 0.05, so anything from 0.04 all the way to 0, you're going to reject the null hypothesis. But if it is greater than your 0.05, you're going to accept it. So 0.06, you're going to blah, 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 blah.
My question is in terms of the significance of the values, the p-value. For example, even if I have p-values which are all less than 0.05, but there are different sizes.
Okay. So you're talking about the strength of the significance. So the strength of the significance can also vary, okay? For instance, if I set my threshold at 0.05 and I get a p-value of 0.49, okay, or 0.049, that would still show a statistical significance, okay? But I could have one that's 0.01, so it's a stronger statistical significance. How we report those in the day-to-day communities is we don't show that difference, okay? But if you are reporting them in academia or in a journal, a scientific journal that you have published in, we put these particular asterisks on those values to illustrate that one is more statistically significant than the other. But those will come later. For now, it's important that you know how to state the hypothesis and the thresholds. Pardon? For now, as we go further, we will have a different explanation. Okay. So, there is another key test we can look at. Okay, this one is looking at two samples, right? And in it, its hypothesis states the means of two samples are equal. You can find all these statistical tests online and all their hypotheses. So you must remember the hypotheses. Okay, so we have here our t-statistic, our p-value that we're trying to generate. And instead of just doing the t-test underneath test 1, we now use underscore individual, and we have both samples now. Okay, both A and B. And we are looking at whether they are equal. Okay, so this equal variance will look at two independent sample tests, assuming that they have a same population variance. Okay? If they don't have the same population variance, it informs you must carry out a different test. But we have just used a random sample that has exactly the same population variance because they are normally distributed. Okay? If we generate the result, we have a t-statistic in this scenario that is negative 0.42, a p-value that is greater than 0.05, and these are the means of sample A and the means of sample B. Okay? So our p-value is statistically significant, but our hypothesis was that these means for the two samples are the same. So now we can accept this hypothesis, okay? Because of our p-value being greater than 0.05. Okay? But we must look carefully when we are looking at each test, okay? Don't always assume that the manner in which the hypothesis is stated for t-statistic is the same for a Shapiro rules. It's not. Okay? So go back, look at those hypotheses. The thresholds are always at 0.05. And check which direction or stated value for the p is. Okay? Okay, so there is another t-test that can also be run. Here we're looking at the difference between the samples, okay, or variables. And this is usually referred to as a univariate test. Who knows what univariate would be referring to? A univariate test. When you are looking at individual variables and you're looking at their distribution, you are carrying variable. You're carrying out a test on only one variable. Bivariate would be two variables. So you could maybe be looking at the distribution of two variables, or looking at the relationships between two variables. Then there is multivariate as we go on, okay, which will be multiple variables, okay? So here, the null hypothesis is stated as the mean of sample B minus the mean of sample A should be 0. And this is what will be investigated in this paired t-test. So it still does have the assumptions of sticking to just 30 values. And how it is done, because it is means that are looking at relativity, so it's underscore REL. And this is what our result gives us. In this case, again, the p-value is greater than 0.05. The t-statistic is negative though, and quite small. So you can accept the null hypothesis, but you can also talk some more about what the t-statistic is. And I would like to see what you guys come up with when you have a statistic that is negative, but your p-value statistic is significant. Any ideas? No? Any ideas? A negative statistic but a p-value that's significant? So that would imply when you have a statistic that is quite small and is also negative, okay? Yes. Okay, go on. So that statistic, because it's negative, would imply that there is no, for instance, here we're not looking at difference, we're looking at relativity in mean. So it would show that it is no difference in the relative means of sample A and B. However, in as much as there is no difference, okay, the p-value is showing that the hypothesis is still true, okay? It's true, but it is quite small. The p-value is more important here than the fact that we have the negative result, okay? So we still discuss it in that manner. We can illustrate that it's a very small statistic or negative statistic, but the p-value does illustrate that the hypothesis cannot be rejected or the hypothesis is accepted. Yes.
Then why then do we have to find the difference in mean if at the end of the day we are going to consider the p-value?
Why then would we look at that? Then we have to look at another test. Okay, now we have to go back. So that's why I was saying to you, any data set you get, you're not going to have only one hypothesis. You're not going to have only one research question. When you will go into, I don't know if you're having the module data science, introduction to data science, aren't you?
Another year.
The other year. Okay, so when you go into that, you will be looking at the fact that with each data set we get, it's a cyclic approach, okay? You will go through these principles of statistics, you know, checking your normal distribution, checking these relationships and so on, having those questions posed. but one goes back and poses another hypothesis. Now in this instance where you have this result, you can go back and pose another hypothesis because of this very result, okay? And then investigate another research question. So this doesn't just stop you here, but that will be more expounded on in data science. Okay, there are also Z-tests in case one has more than 30 samples. Okay, so instead of using the t-test, you can then use the Z-test that also look at the means of samples. So I won't go through these. I think we're running out of time. 47. Okay. So in here I have also put for you. And when I write hypothesis testing, I'm talking about need for you to know what the null and alternative hypotheses that you're investigating within these tests are. Who can remember what the ANOVA test does? ANOVA? To which categories? Okay. So it would be looking at a relationship, okay? But it can look at the relationship between the continuous and categorical variables, or it can look at the relationships between groups within a categorical variable, for instance, or and a continuous if you have two different categories. Okay? So now if you think of that sampling approach where you have different groupings, a lot of the time you'll be using ANOVA tests within it. Okay? Who can remember what the chi-square test does?
Two categorical values.
So categorical variables. So do you know the hypothesis behind it?
Well, I know that we just get a p value and we look at if the p is less than.
Yes, but now you have to go back and know all the hypotheses. Okay, the hypotheses of Shapiro-Wilks. Who's heard of Kruskal-Wallis?
I don't have
I know you want to just stop at the ones that you already had in class, but that's not the experience you're supposed to have. You're supposed to know as many as you possibly can. But also what's key is go read up what is a parametric test. What is a parametric test? Parametric. And what is a non-parametric test? And give examples, okay? You have mostly worked with parametric tests with the exception of one non-parametric test. When would that have been? I'll give a hint this way. When you were running the Shapiro-Wilks test, it had a sample limitation, right? Okay, but you had discussed it. Yes. We discussed Shapiro-Wilks.
But you need
Yeah. And we said it had a sample limitation of what? It had a sample limitation of 5,000. You couldn't work on a data set that has more than 5,000 samples. And so there was an alternative test that you could use to Shapiro-Wilks. Has the Russian name, the Kolmogorov-Smirnov test. I'll ask Charles to put the okay, but you had it with me in class when I was talking about normal distribution.
And then we need to go back.
We didn't go back over the months. Yeah. Okay. Now you'll go back over the months. Okay.
So where are the ANOVA because we used to be ANOVA teachers here last week. So where are they for parametric or undergraduate?
This is what I want you to do, Father Regional. Yes, yes. Okay.
By the year, and is the 21st program is going to go next time.
Okay, so I think we have 8 minutes. I wanted to go through something practical, but I think you can do that on Thursday. Are there any questions?
But also for some of the scale that the GPs are not going to generate will not be with the sources like everything one small part of
Okay. So as far as visuals are concerned, you will have a module on making visuals and storytelling. That is not our goal here, okay? Within this particular course unit. However, our goal here was to have a bit on the key rules of which visuals apply to which types of variables. Okay? If you're generating a visual for distribution, which is what we use for our continuous variable. I love this class. Yes, or a categorical would then be a count plot, a box plot can also work, or a bar plot more. Okay? And then if you're looking at the relationships, it depends on the different graphs also vary. Okay? That's what's key here. As far as beautification and storytelling, that will be done in another module when you get to that. But the question was?
Yeah, my question was on how to determine which specific users are best for your data.
That is already, is a rule in statistics already.
Not like we said, for example, where you have more than one visual to be able to predict what you are showing and determine which of the two visuals is better. But also changing the scale.
So again, like I said, that will be another module, but what's important here is having the rules of which graph applies to which variable. Which graph applies to which variable. So now it's fine. This is not a visual storytelling class. This is rules of statistics. Because if you don't have this background, you will struggle and generate any type of beautiful graph on the other end, but it will never make sense. Okay? Because you will notice in Excel, you could generate all types of graphs, right? Any type would work. But Excel also had the ability to create for you the recommended graphs. You noticed?
Yes.
How was it generating those as the only recommended? Because there are statistical rules about which graphs apply to which types of data. And these are the ones we stick to here until we can progress to the other one. So, you will continue continue with the inferential statistics on sampling and some of those statistical tests on Thursday. And then we must have a test. Yeah, we're supposed to have a test. Yeah. So can we push our test to Thursday instead, since now our I forget the days. So Tuesday?
Next week.
So Tuesday we'll have a test. And then regarding the little poem quiz, I noticed some people struggle to put their attachments. So if you're struggling putting attachments on your Moodle when you're doing the test or on Canvas, okay? Because Canvas is quite similar to the system on Moodle. Please go CUIS and have this issue sorted, okay? It's just learning the